So welcome everyone to the Atto Fridays. Our speaker this week is Professor Eva Lindroth. She received a PhD from University of Gothenburg. She was a postdoc in Oxford and has been in Stockholm since the mid-90s. So she has a long track record in our field. And she is interested in atomic many-body physics in structure and dynamics. So it's a pleasure to have her here today. So thank you so much for joining. And today she'll talk about photoionization delay in heavy atoms, spin dynamics, and angular dependence. So if you're ready to start, we're ready to listen. The floor is yours. Thank you for joining.
Thank you very much. I start with sharing the screen here. So takes a few seconds.
And you're on speaker view.
So, do you see it?
Yes.
Yes. Okay.
Perfect.
Yeah.
We're ready to go.
Yeah. Thanks a lot. It's really nice to have been invited to Atto Fridays. So what I would like to talk about today is photoionization delays. And I will start with sort of the basics and what it is and how it can be measured and so. And then we'll go on to some recent developments. So what we are interested in here, that's really light-matter interaction. And especially the process of ionization, which is, of course, a very important process in many aspects. And when we have an electron wave packet leaving a system where it comes from, we know that it is just a wave packet, and this is a wave packet characterized by an amplitude and a phase. And of course, physicists has been studying the amplitude for, I don't know, perhaps more than 60 years through the process of photoionization. But much less has been possible to get to know about the phase. There is some ways where you with traditional methods that you can get phase information of your wave packet, and one of them is this when you look at the angular dependence of the photoionization cross section. And I will come back to that a little bit later. I will come back to this in more detail later. And another way of getting phase information traditionally is to look at resonances, where we have this Fano profile, which you can see in the background here, which is really the asymmetry of this profile that's coming from interference between different path from the same final state from the same initial state to the same final state, one through the resonance and one just to the continuum. And so this is the phase of the different paths which creates this amplitude. But still we can see that there is much more to learn about the phase. If you look at this picture here, which is of course a calculation, it describes the time evolution of the wave packet when electron is ionized from a resonance in helium. And you see here on one axis is the energy, and on the other axis is the time. For very short times, the profile of this wave packet is just given by the profile of the light pulse. So this is ionized with the light pulse. But when time goes on, this ridge is built up. And finally, when you go to infinite times, you reach this Fano profile. But from this calculation, one can see that much more is going on. There is a lot of ripples and things happening here. And if this is a more complicated resonance where you have different decay paths, for example, it is all these details which determines which quantum path is taken. So this is sort of very interesting information which one would like to get hold of. So this is sort of a main question. How can we get more phase information than what these traditional ways have offered to us? So this is a short overview of what I will talk about. I will talk about the phase, how it can be measured, and the connection between the phase and that what is in the title, the photoionization delay. And of course, the reason why I'm talking about this in the Atto Fridays is that here attosecond techniques has given us new paths for phase extraction. Later on, I will talk about some new developments. One is the angular dependence of the delay. And another one is some interesting things you can see for resonances. And if we have time, I will say something about bound resonances as well. I would like to start with just giving a short description of the relation between the delay and the phase. So this can be understood very simply. So if we have a free electron in empty space, then it has this simple wave function. And we can compare this to another electron which has passed over a potential well. And in quantum mechanics, of course, we know that this electron which goes over the well, the wavelength will get shorter. So if we compare the two cases afterwards, there will be a phase difference, and this is what is called the scattering phase. This situation with a particle going over potential, if we think classically, we know exactly how to treat that. And if it's a simple potential, just a square well potential, then it's also simple to calculate. And one thing one can calculate is the time the particle is delayed when it goes over a potential. Actually, in this case, when it's a potential well, it will not be delayed, it will be advanced, because when it goes over the potential well, it goes faster. And this is easy to calculate. It will be proportional to the strength of the potential, to the extension, and then divided by the speed, the cube of the speed. So if we now turn to the quantum mechanical case, then what we have is this phase shift. And in the 40s and 50s, people like Wigner looked at this more carefully and showed that you can, from the phase shift, you can create the quantity which corresponds to this delay. And what you do is that you take the derivative with respect to energy of your phase. And to get the right dimension, you multiply with h bar. And actually, if you do this in this very simple case, just the square well potential, then you get the same as in the classical case. You get that depends on the strength of the potential, it depends on the extension, and then in the denominator here, we have something which is very close to the speed of the photoelectron. So this quantity, delta t here, one usually call it the Wigner delay, and it has to do with a delay which a particle get when it passes over a potential. So of course, this is connected to a phase, so you cannot measure it directly. Phases you can only measure relative to something else. And now comes the Atto technique contribution. And the example here will be from the method of rabbit, which is one protocol, so to say, which is very much used. And the rabbit stands for resolution of attosecond beating by interference of two photon transitions. It's a complicated acronym. And then the protocol is like this, that with you start with a train of attosecond pulses. And if you look at this in the frequency domain, this will be a comb of harmonics. And these harmonics, they are odd harmonics of the driving laser field, because this train is made by high harmonic generation, and that's how high harmonic generation works. So shining this comb of harmonics on your sample, you can take one of the teeth and ionize with it, or you can take another teeth and ionize with that. Now, when this is done in the presence of the driving laser field, little omega here, it can happen that the electron, when it's already in the continuum, it picks up another, it absorbs another laser photon, or if it was this electron, it can be stimulated to emit a laser photon. So in this way, we reach the same final state. So here we have a classical situation for quantum interference. We start from the same initial state, we go to the same final state, but through two different paths. And of course, these paths, they will then interfere with each other. And if one, for example, change the delay between these two light fields, then the probability to find electrons here in the sideband will go up and down. And this is an important name. This is called the sideband, this electrons which comes at this energy. So in the theory here is in principle rather simple. The probability to get electrons in the sideband is the sum of the amplitudes through the what we call the absorption path and the emission path. And of course, we have to take the modulus square. And because we have the cross term here between them, we have one term which will be oscillating with the phase difference between the two paths. And one can understand exactly what argument you have here. One term comes from the delay of the two fields, which you have control over when you do the experiment. Another term comes from the delay between the different attosecond pulses in the train. This is not something you know very much about, but it can be cancelled by taking differences between different measurements. And then finally, there is something which is usually called the atomic phase, or if you multiply it with 2 omega for the atomic delay, divided by 2 omega by the atomic delay. And that is a quantity which is characteristic of the system. So this is the interesting quantity. And it sort of is very similar to this delay which we have talked about, because it is a difference between two phases with a small energy difference, so like a derivative. So if you want to understand a little bit more about this, you can do a calculation with hydrogen, which is not so hard. And this is done here. Here I have 3 curves, and it shows the phase as a function of electron energy. And it's really the phase, not the phase difference, because this is theory. So the blue line here, that's the absorption path, phase in the absorption path as a function of electron energy, and the red is in this emission path. If we were really interested in to compare with what Wigner and others did, which we are, then what we're really interested in is how we come to this middle state, the sideband, how we would have been coming there with 1 photon, because then this is the pure case, so to say, and that is given by the gray line. Now, turning more to what you can really see in the experiment, we have to look at phase differences. So we take the difference between the phase in the emission path minus the phase in the absorption path and divide with 2 omega. And then we get the blue line. And then we can compare that to the derivative of the gray phase in the previous picture. And then we get this line. And you see, this is really a big difference. So what we get in this experiment is not really this Wigner, the gray phase, is this atomic. It's not the Wigner delay, it's the atomic delay. And the red one is just the difference between them. So this sounds at first as bad news, because you wanted to measure something and what you got was very much affected by an unknown effect. But it turns out that the situation is not so bad, because this difference, the red difference here, that's very similar in different systems. And this has been shown with calculations which can be checked by experiment. And then you can see this on this picture, how similar it is for different systems. So this in the left figure here shows this difference, just the red curve in the previous case, for different elements from argon to radon. And this is only for p orbitals, but it's actually the same if you look at s orbitals. And you can see that they all very nicely fall on the same curve here, showing that this contribution, extra contribution from the second photon, is to a large extent universal. It depends on the kinetic energy, of course, that's the main thing, but it also depends on the long range potential. So when I say it's universal, I mean it's universal for electrons leaving a singly charged ion. So to calculate this continuum transition, this effect of the second photon, that's not so simple, because it is you have an electron in the continuum, and then it absorbs an extra little photon and gets to another continuum state. So it is a continuum transition. And if you have tried to do this numerically, you will know that such integrals, they do not converge in any finite box. You need to somehow be able to integrate to infinity. But there are tricks for this, I will say very shortly afterwards. But first I want to show that it's what we got is really close to what one can see in experiments. This is an experiment by the group of Anne Huyer, who I know has talked on an earlier Atto Friday a few years ago, and they studied this photoionization delay in neon. And here in this picture, you see the difference between the delay for an electron coming from the 2p orbital or one coming from the 2s. And this was like a breakthrough, this experiment, because they could, by an increased energy resolution, they could really isolate the interesting effect very well from and get rid of shake-ups, as it's usually called. But here you can see the different energy values they measured, and they lie very nicely on this black curve. This is exactly our calculation. So this shows that we do understand the continuum transition, and because of that we can sort of compensate for it. I wanted to say a little bit about what kind of theory it is. I will not go into details, but just say very quickly. So of course, what is built on here is the knowledge which people have acquired during many years about photoionization. And then when it comes to photoionization cross sections, it's well known that it's not enough generally to just use single particle models like Hartree-Fock. And this is illustrated here in my picture, where we see the experiment. And then what is the answer from Hartree-Fock, and you see that it's completely wrong. One can try to improve it, and here it's done with what is today usually called CI singles. That means that you say that you now, as in this example, we ionize from argon 3s, and then we know that we have a channel coupling between electrons coming from 3s and from 3p, and if you include that, you get something better, because you get this big dip, which is in the experiment also, but it's not really relying correctly in energy. But already in the 70s, there was another method developed, which has this CI singles, but on top of that, some more effects. And it usually goes under the name random phase approximation, with exchanges E. It's a historical name. And it's has been proven many times that this method gets the photoionization cross-section more or less correctly. There were pioneers of this, was, for example, Amusia, who recently passed away. You can see that there is still, of course, things which can be better. Here there are some structure, which is probably shake-up resonances or so. And they are not described by this method, but the overall structure is very good, and that is a good starting point. Now when you have to calculate photoionization delay and calculate the whole process for the atomic delay, the 2-photon process, you can start with this random phase approximation and then just add on a photon. And for those of you who are interested in diagrams, you can see what is included. For the others, I just can say that the simplest way you can do it is just to take your random phase approximation produced outgoing wave and then add on the last photon. But later on, we have also done full 2-photon RPA, showing that the first one to the left here is a very good approximation, actually. So I said this, that it's not so easy to calculate the continuum transition, because you have an integral which doesn't converge in any finite box. And there are different ways to do this. What we do is that we use a method which is called exterior complex scaling. And then when we do the second integral, we integrate first along the real axis, so until we are so far out that we know how the wave function look like. We don't know, we have to get from our calculation the phase and the amplitude of it, but we know the form of it. And since we know the form of it, we can do the rest of the integration analytically, and we do that along the imaginary axis. And there are other methods to do this, but they all rely on the same thing, that you know something about the continuum wave function far out. Okay, so this was my starting, and now we go to some newer developments. And I want to start with the angular dependence. And we have to take a step back first and think about angular dependence on the photoionization cross-section. And what we mean here with the angular dependence is that we have the laser light, and it has a polarization axis. And now we look at the photoelectrons, which comes out with respect to this angle to the polarization axis. And already in the 60s, people understood that you could summarize what you get in this nice formula, which says that the photoionization cross-section in a certain angle is obtained as the total photoionization that is integrated over all angles. And then you have a Legendre polynomial, and then you have a parameter here, which goes under the name beta parameter. And in the interesting cases, the beta parameter is energy dependent. In ordinary photoionization, one photon photoionization, it's not the sum here, it's just one term. And then it's called beta 2. That is what you need if you have dipole, light, and just one photon. I don't want to scare you off now with the equations, but I would just like to say very quickly what is hidden in this beta parameter. So you have to think about a photoelectron leaving an atom or any system. Of course, it's valid for molecules also. And then you know that you will have a plane wave far away from the system. This part just depends on the kinetic energy. And then you will have a matrix element, which is the matrix element from the ground state to the continuum state. And then you have the scattering phase, and then you have a spherical harmonic. So to get the cross section, you have to take the amplitude square of this. And of course, this term just disappears, just gives unity. And also in all, here we sum over the angular momentum, and in all square terms here, also this scattering phase disappears. But in the cross terms, this scattering phase survives. And the difference in the scattering phase is weighted with the matrix element for the different channels. So this will be for one of the channels, and this will be for the other of the channels. And because of that, it will vary in energy. So this is the interesting thing. From these beta parameters, you get information about the scattering phase, and you get information about the relative strength of the different angular momentum channels. So what about delays? Yeah, a few years ago, Ursula Keller and her group, they did the first, to my knowledge, the first measurement on how the photoionization delay varies with angle. And this is one example from the paper. What they measured was the angle, the time delay for a certain angle with respect to the time delay for the particles going in at zero angle. And you can see that there is the blue ones here are the experiment, and you can see that there is a clear angle dependence. And if one look, this is for a particular sideband, so a particular kinetic energy of the outgoing electron. And if you look at the other sidebands, the other energies, it's slightly different. So here we have an interesting angle dependence. It depends on energy, and will give a new route to similar information as you would have from the old cross-section measurements. So how can we understand what happens here? First of all, of course, it was a little bit surprising that you got this interesting angular dependence from helium, which only have s orbitals. So if you have one photon, you can only reach p, and that means that you have always p. You have no interference between different channels, so the angular dependence will be the same in every channel for every energy. But then one has to remember that if you do a delay measurement, either you do it with rabbit or with other methods like streaking, then you always have at least two photons. So the photons you will measure will not be the electrons you will measure. They will not be the one which have just absorbed one photon, but they will have absorbed at least two photons. And then you have already two channels and the possibilities to interfere. So if we would be able in the 2-photon cross-section, then we can use this formula, which we just discussed, and we know that now we need to sum over, because we have 2 photons, we will have 2 contributions, 2 betas, the beta 2 and the beta 4. But now we were not really interested in the cross-section. We are doing a rabbit measurement, and we have an absorption amplitude and an emission amplitude, and it's the cross term which gives information about the delay. And to analyze it, one can do similar as one did for the photoionization. And you will see that you get also very similar things. You get the spherical harmonics, and you get the scattering phases. But now the matrix elements are different here and here. And this has one interesting consequences, and that is that the beta parameters will now be complex. Otherwise, it looks very similar. This signal, which you are after in the experiment, can be written as the angular integrated signal. So that is the delay of the angular integrated signal, if you want. I mean, it's related to the delay. And then you have the same expression again, just with this complex betas. But the betas themselves, they are calculated in the same way. I mean, that they are sums of and the relations between the different matrix elements, and there is some constants, and the constants are the same. It's just that the matrix elements are different, which makes them complex. So this is the signal, but to get the delay, we take the argument. And so we take an argument of a product, we get the sum. So the delay in a certain angle, that will be the delay of the integrated signal plus a difference. So this is a way to really analyze this type of experiments, which is very neat and very much in line with what we have learned from photoionization studies during many years. And I think this is a good illustration of that the phase is really a new aspect of, and it's new, but a phase, an aspect we now have access to, but it's of the same physics as the amplitude. So what can you do with this information? I just want to say a little bit, which I think is interesting, that you can perhaps use it to separate the Wigner and the atomic and the 2-photon contribution to some extent. And to show this, I would like to take a heavy system. So it's still from an s orbital, but now it's from xenon. And I said before that when you ionize from S, you can only go to P, but of course, in a system like xenon, there is a difference between the P1/2 and the P3/2. So you have actually 2 channels. So due to relativistic effects, you can have such an interesting angular dependence already after 1 photon. And then, of course, again, after 2 photons, in the same way as you could for helium. Exactly as the argon I showed you before has had this minimum. This is called the Cooper minimum. This is something which you have also in xenon. You have it in all rare gases apart from neon. And this is a place where this is the cross section again. And I just want to show the Cooper minimum. And this is a place where the cross section changes very quickly. So it's an interesting place to look for effects. And so if we look at the Wigner delay, this is a calculation, of course, again, in this region of the Cooper minimum, then we can see that we have a very strong angular dependence. What is shown here is the difference in a certain angle, the difference between that and the delay of the integrated signal. And you see how it goes up and down and has a strong energy dependence in this region over the Cooper minimum. But there is an interesting case in all this, is that that the Legendre polynomial for a certain angle, which is 54.7, is 0. So at this angle, there is no energy dependence. They all have the same. It's the same in the photoionization cross-section, and it's called the magic angle by tradition. So the Wigner, so this looks interesting, but the Wigner delay is not measurable. So we have to look at the atomic delay, which one can measure. And this is the result. You see that here we have also something very strongly happening at the Cooper minimum, but at very low energies, we have something more happening. And it's not so surprising, perhaps, that this, which we have also, although it looks slightly different, in the one photon case, this is coming from the first photon, the XUV photon, which ionized the system. And this is an effect of the second photon. Perhaps you don't think it looks so promising, but if one plot it slightly different, exactly as Ursula Keller's measurement was done in 2016, so we plot the delay in a certain angle compared to the delay in 0 angle, then it looks more interesting, because here you can see that in this Cooper minimum region, we have the same result for the atomic and the Wigner delay. This is for 30 degrees, this is for 60 degrees, this is for 70 degrees. Here at low energies, we have a strong effect of the second photon. But here in this more physically interesting region, we have not. So this is perhaps a possibility to separate the effects also in experiments. I talked in the beginning a lot about this, that the CC delay, the continuum delay, is universal. So one can ask oneself, is this still true now when we have the angle dependence? And actually it is true. Here you, at least to quite some degree, here you see the result for krypton and for xenon. So it's different orbitals. And here you have 60 degrees, and here you have 70 degrees. So it's different in 60 degrees and 70 degrees, but it is the same for the two elements. So you still have a universality, even though you have your angle dependence. If you go to extremely large angles, there it starts to be a difference. So of course, this universality is not a perfect truth, but it holds quite far away. And it's also this that what happens when you have very large angles, close to 90 degrees, is that you do not get very much many electrons out at all. So this is the so it's hard to measure this, although it might have been interesting. Okay, so I would like to switch subject and talk about the other case where you have some effect of the phases already in traditional measurements, but where you can get more when you do attosecond measurements. And that is resonances. And I will talk about an old friend. That's the giant resonance in xenon, which has been studied since the 60s at least. And this is an experiment by Becker et al. I didn't put it up here, apparently. And it's just over the 4D threshold in xenon. And you see that it's has a very large cross-section, but it's also extremely broad. So the lifetime of the resonance behind this is very short. To make it more clear, I have this picture here showing that you need around 60 EV to produce around 70 EV to produce the holes. in either 4D 5/2 or in 4D 3/2, and they have a small difference here of 2 eV. It's not so small to be a fine structure, but it's small compared to 67. There are many interesting effects with this cross-section. Not only is it huge, it's also very strong, very big difference between the partial cross-section to these two channels. You can see that here. So the blue is the 4D 3/2, so leaving the atom in with a hole in 4D 3/2, and the red leaving the atom in with a hole in 4D 5/2. If one take the ratio between these two cross sections, it has this strongly varying signal, and this is also seen in experiments, so it's not just theory. There is I put here the non-relativistic ratio. That's what you would expect in a non-relativistic calculation, because there are 6 electrons in the 5/2 and just 4 in 3/2. So this is the ratio is 1.5. But the truth is very different. And people have for a long time tried to visualize what happens with this in the case of this giant resonance. And one popular way to look at it is to say that when you ionize from 4D, the dominating channel is that it goes out in F, and the F has a very strong angular momentum barrier to go through. And one can do this simple-minded pictures showing how a Hartree-Fock potential would look like without the centrifugal potential, and then how it looks with the centrifugal potential. And then we can see that you can trap something behind this potential. So with theory, you can do many things. So one thing which one can look at is to sort of follow the cross-section, how it builds up when it goes out through the atom. So I mean, the cross-section, that is the probability current, more or less, of far away from the system. But of course, this probability, when you go sort of inside the atom, this probability current changes. Finally, it flattens out. That's the cross-section. So now I looked at it for different radial distances, very close. So this is in Bohr radii. So this is 1, 2, 3. And here we have, we give the system a certain energy, and we follow the two channels. And then what you expect is a negative probability current, because that means that something is leaving the system. But actually, one of the channels here is going the other direction. So it's really like you have this potential here, which we see here, and the particle starts to go out, but then somewhere they collide with this potential, and then they one of them go back and the other one have an increased probability to go out, something like that. And we can follow how this changes when we change energy. So if we have a little bit higher energy, it's still the same general trend, but it's different. But if we go much higher energy, then they look more similar. So this is really that one can think about is that they go over the barrier. But it's even more interesting than what one can think first, because it is the one with the highest energy which is tending to go inwards, and the one with the lower energy which is more likely to go outwards. So this is like there must be some interesting interference effect here. And the only thing which one can think of, I think, is some kind of resonance. And of course, we just talked about the giant resonance. This is very large, so it must be an allowed path out. So it is a singlet p resonance. You can see that also when you do calculations. It's allowed non-relativistic. Actually, it's probably 2 resonances, but that's nothing you can see. You just see one blob. But when you look at it relativistically, you will always have also the spin forbidden cousins, so to say. And this is what we have here. So in addition to this giant resonance, we have resonances of triplet D character and triplet P character, and especially the triplet D one is very active. So one can look at this resonance as a switch. So this resonance is populated, and because of that, there's a possibility to change from one of the channels to the other. Yeah, now there was a lot of theory, but of course, and it was a lot of cross sections. But one could wonder, can you see this also in the time domain? And yes, you can. So if we tune the photon energy to this triplet D resonance, then these pictures of the rate would look something like this. And then we can look at the atomic delay. And here you can see large variations of the atomic delay in either the 4D3 half channel and the 4D5 half channel. This peaks or valleys of it, they come at different points because this is now the electron energy. And when you populate with a certain photon, meaning you're hitting the triplet D, you go out in slightly different energies. So there is a chance one can see this. And of course, this has been tried. So this is again a measurement from Anne Huyé's group in Lund. And this is the experimental data. It's you cannot understand what it is, but it's actually what you see here is a 2-dimensional plot or a 3-dimensional plot where you have the slow electron here, which is the photoelectron. And since these are auto-ionizing states, you also have a fast or shear electron. And by looking at them in coincidence, it has been possible to disentangle the different channels. And what do we get? Yeah, you can see the experimental results here in the red dots. Here is the upper one is the 4D3 half, and the lower one is the 4D5 half. And you can see that the difference in delay for the lowest energies here is like 100 attoseconds, or over 100 attoseconds. So it's really, I think it's really interesting that you now have a sort of a new tool to look at your at resonances of this kind, because you can look also in the time domain. Of course, one could have wished that the error bars would have been smaller and that the agreement would have been better. But I think that this first result still shows that there is a qualitative agreement between theory and experiment, and I'm sure we will see more accurate experiments in the beginning and in the future, and then we will probably have to do more calculations. But I want to say a little bit about what can be done now when we have both phase and amplitude. And this is again something from the group in Lund, David Busto and Anne Huyé. And they have shown that they can take their experimental result and construct the so-called Wigner distribution. What they do is that they measure these amplitudes, the absorption and emission amplitudes. They take the Fourier transform of these, and in this way they construct the Wigner distribution just from first principle, so to say. And here they have done that with experimental data. Again, this is helium, and it shows very much similar like the first picture I showed from Luca Argenti's calculation, but now it's from experiment. It's the doubly excited state, lowest doubly excited state in helium. And you see that for short times, you have a blob here, which shows the pulse, more or less. But when time goes on, you get interference, and some parts get down, and some part gets up. And you can really follow the evolution of this electron wave packet coming from this resonance. In the case of xenon, the experiment was not so accurate that this could be done, but we could do the same thing with the theory. And this is what you see here. It's again the Wigner distribution. So it's the time here on the y-axis, the energy on the x-axis. And here you can see the, for short times, you see the population of the giant resonance of this shiny thing here. It is short time, but broad in energy. And here you can see narrow red thing, which is narrow in energy and long in time. And this is a sign of these other resonances, the triplet D resonance, which has not been seen in experiment directly. You can just see the effect, for example, the effect of that you have this unusual relation between the two channels. So I think my time is going to an end, isn't it?
We are quite flexible, so it's your call.
Yeah, I have. So should I skip the last part or should I go on? It's
again, if you feel like going on, go ahead.
Yeah, it's not so many minutes. I just wanted to say something about another very new development, which has been done by several experimental groups over the very recent time, and that is to look at bound resonances. And then, so you have this case is from helium, so it's not heavy systems. And you have now in your absorption path, the first photon, the first harmonic, goes to a resonance below this ionization threshold. And then the IR photon ionize. And then you compare that with the path where you go in the more usual way to continuum state, and then an IR photon is emitted. So it's the same, the rabbit principle, but one of the paths is below threshold. And the results I show here is from a paper by An Huyes group again, but it has been studied also by Racking's group and by Pascal Salière, at least. Perhaps it's even more, which I'm not aware of. So one can think about what we have here, because when you go through a bound resonance, then of course you have something which is proportional to the energy, the denominator, where you go from the ground state and you put on a photon and then you go to the resonance. And here, of course, you have it goes to zero at some point. And if you look at these matrix elements in lowest order, so without correlation, then you have these extremely sharp peaks at the resonances, and it jumps from one sign to another sign around the resonance. This is, in this case, is the 1s4p, and this is 1s5p. But interestingly enough, there is also, of course, it has to be like that in between the resonances, they will also change sign. So if one look at this in a better calculation, so that one have include types of correlation, which I've discussed before, then at the resonance, you still have this very sharp jump. But between the resonances, the two channels, the S channel is blue and the D channel is red. The two channels, they separate in energy, so they go through zero at different points. And this will have significant impact on the angular dependence. It's not so easy to see directly from such a picture like this what the angular dependence is, because of course you have to weigh the matrix element with the spherical harmonics, for example. But we have tried to, or one of the co-authors have tried to make a nice picture which try to show this, and I will say a little bit about it. So what you see here is the energy of the photoelectrons on the x-axis, and then you see the angle here. So it's a polar plot. 0 is this is 0. And then when you change from purple to yellow, you make a pi jump, you change sign. And this is the theoretical picture, and this is what they have been able to secure in the experiment, showing that some things are similar. So we see that here the dashed lines, they show the measured values. There is a slight red line here which you perhaps see, and that is at this 1s4p resonance, and there you have a sign change everywhere, so the angular dependence doesn't give you very much. But at the anti-resonance, the places in between, perhaps I should show, the anti-resonance is these places in between where you go through 0. That is given very much by the green line here. And there you have this detailed interplay between the S and the D channels, and there's a very strong and fast varying angular dependence. So and this picture just shows the channels, each of them, and one can try to see how it all fits together. I just wanted to show this because it's a very new development, that you look at, really also look at what is below threshold. So thanks a lot for your attention. What I wanted to say today was, first of all, that when we have quantum mechanics, we can learn a lot about the dynamics of the system from the phase of the wave packet. And in the later pictures here, where we looked at the Wigner representation, for example, I wanted to emphasize that when we have both amplitude and phase, this means that we have a more complete characterization of the wave function, and that we can also reconstruct what happens in a more complete way, in a more full way. And of course, there have been observations of phases long time since, like these asymmetry parameters and the Fano profiles, but now we can look at many more aspects. And perhaps in the future we can use phase control and determine more what happens in quantum mechanical processes. And I personally like very much this, that one can watch how spin changes, as we did in the xenon. And it's always very interesting what the resonances can do. So thanks a lot for your attention. I wanted just to, this is people who in different ways have contributed over the years to these things.
So thank you so much for this really nice talk. We really appreciate you speaking to us today. Are there questions, comments? Do feel free to write in the Q&A tab or to raise your hand. And while the questions are coming, I will use the opportunity to make a few announcements. We are already putting our program together for the Quantum Battles in Atto Science 2023. And we have chosen our topics as well. So they're going to be how quantum is Atto, which fits well into today's talk. Also, the Atto science of solids. And we're also going to talk about or make a session about chirality, symmetries, and molecules. I see some questions coming. Anne Hart, thanks for the nice talk. What is this magic angle at slide 45?
Yeah, the magic angle is 54.7 degrees, and that's where when the Legendre polynomial is 0. So should I share the screen perhaps again?
Yes, go ahead.
Takes us some time. This.
Okay, I've allowed also you to speak, so if you would like to follow up, do feel free to unmute yourself.
Yeah, thank you. Thanks again for the nice talk. Actually, I wanted to know where this magic angle comes from.
Yeah, it comes from here. It is. It comes from this in the when you look at the angle dependence of the photoionization cross section, you have this form. And and of course it's not obvious how this form comes, but one has to go through it to understand it. I mean, to really understand where it comes from. But this is if you do ordinary photoionization, it's the n equal 2, which the only one which contributes to single photoionization with the dipole. So you have beta 2 here, and then you have p2. And so this is the second Legendre polynomial, and that is 0 at 54.7 degrees approximately. And when you have, so when you are at that angle, you have the same. I mean, if we look, and I have it now. I had it for the delay, but it's the same thing. You can see here. I mean here we look at the delay at different angles, and they all have an energy dependence. But at the magic angle, because this this expression is 0, you don't have any energy dependence.
Yeah. So when you consider now multiple photons in the continuum, then this magic angle will change because you have higher orders of the polynomial, right?
Yeah, so you don't have a magic angle anymore. So here, so this is when you have. As far as I know, this only exists for one photon. So when you have two photons, I just called it the magic angle because it's the same angle. It's the same, but it's not magic anymore because here you have an energy dependence everywhere. So this will not save you in the multi-photon case.
Yeah, thank you. And can I actually continue with one more question? Yeah. So I also have a question to the Wigner representation.
Yeah.
And I think it was in helium. So it was a calculation in. It was the calculation. Yeah, exactly the theoretical one. So on slide 14. 40, sorry. So next slide, please.
Next one, okay. Yeah. Yes.
So I think it's actually also a very beautiful representation. I'm just wondering, or always I forget, because we see now this hyperbolic feature there, and this tells us that there is a coherence between two paths, right? So, or I ask differently, what do we learn from this interference pattern, which we see when we are going away from this resonance? So, for example, at 800 electron volts and the time between 200 and 400 attoseconds. So there we have this. So what do we learn from this pattern?
It's not so easy to. I mean, I don't think the interpretation is so simple. Can I go to the first picture because it's here. I mean, this is not a Wigner representation, but it's a similar thing. So this is from a calculation, and here you also have this with the time and the energy, and it's what you can understand the beginning, because that is given by the pulse, and you can understand the long time, because that is what you traditionally measure. But I think that these ripples which builds up here during intermediate times and at different energies, I mean, this is like following what happens in time.
So it's not okay.
So what you would learn, I think, is that if you want to steer something, this is what you need to be able to control. If you have a case where you have different channels, then from the beginning you have this broad thing, and then you develop different paths, and then so you need to understand all these details to be able to say, to predict, we can say, to start with, to predict where it will go.
Yeah. So
sorry.
Yeah. No. Then yeah. Thanks for that. Picture. I think I'm so at the moment when I look at this one, this looks for me like two pulse interferences. And when, of course, when the pulses are close, then the oscillation frequency is less. But okay, I will need to think about.
But this is not the pulse interference. I mean, this is helium ionized with one pulse. So it's just theory. So it's just one pulse, but it's two. But it is it is the I mean, in this case, the pulse populates the resonance, but it also populates the continuum directly.
Yes.
So it's the interference between those paths. Yeah.
Yes. So, but then I wanted to say then it really looks like interference pattern, which depend on time delay. But I need to think about this more, maybe.
I also need to think about it.
Thank you.
I don't have perhaps I didn't have a perfect answer.
Thank you very much.
Thank you.
So are there further questions, comments? Would anybody like to ask something? Again, raise your hand or type your question in the Q&A tab. Now, I don't see yet any coming. One question that, I mean, if you talk about phases and you talk about resonances and time resolution, something that occurs immediately is the coherence. So for these pathways, and given that they're not isolated, but that you have all sorts of other things going on, what is the role of the coherence, and how do you avoid it or maybe use it in your favor?
Yeah, of course you have in principle a coherence between the outgoing. Is that what you talk about, the coherence between the outgoing photoelectron and the target left behind?
Yes. Or also maybe different degrees of freedom, because you have also different angular dependencies. And for instance, that experiment by Busto et al., they analyzed two pathways, and they showed that the other degrees of freedom of the electron could lead to the coherence in principle. So, I mean, could be the target, but could also be degrees of freedom. So what is the role that it is playing in your work or in the resonances that you have shown?
Yeah, of course, but yeah, I think, I mean, this question about coherence and how long you have established this coherence is a very interesting question, and there are much more coming up now where people are interested in this with the holes. I mean, sort of, perhaps I didn't say it so clearly, but in this helium case, you ionize with a broadband laser, so that you ionize at the same time several resonance, for example. You can also think about ionizing at the same time two fine structural components, and then so you have really coherence between the different wave packets. yeah, I haven't looked so much about that. When you do quantum, traditional quantum calculations, you have always perfect coherence, so to say. So the interesting thing which one has to study, and I think this is a very important thing, is to look at this when you lose coherence. I mean, how you gradually lose coherence, and what you can say then in this in between times. That's what I can say at the moment.
Okay, but it is already quite nice. So thank you so much. I can see, I mean, people are a bit quiet, but we had some interesting questions as well. So if you would like to ask questions privately, we're going to stop the YouTube transmission right now. And we are also going to stop the streaming. So if you would like to have a chat, but you are a bit shy, you don't want your question all over the internet, which we can understand, right? So just hang in there, because we are stopping the transmission. For all of you who are watching on YouTube, take good care of yourselves, stay safe. Thank you for joining. And let's thank also Professor Lindroth again
Thank you.
for a really nice talk. And hope to see you soon. Next week, we have hot topic section, which is going to be a bit of a mix of machine learning and X-ray. So
interesting.
Yeah, it looks promising. So support also our early career researchers, and have a great weekend. And